Good morning dear students, myself Sachin S. Pawar and I welcome you to my 10th video on Unit 5 States of Matter, Gases and Liquids. In the present video, we will be dealing with behavior of gases. Okay, so we have learnt an equation of state. So, from here on I will start equation of state. So, we have an equation of state that is known as PV is equal to nRT. This is also known as ideal gas equation. Equation of state or ideal gas equation. Ideal gas equation. Now, why it is called ideal gas equation? Now, this equation when we have derived it from, we have derived this equation from Boyle's law and Charles' law. Boyle's law, Charles' law and Avogadro's law. Okay. So, now here is the time to apply this. So, we are considering behavior of gases, behavior of gases, behavior of gases. Let us continue with this. Okay. Now, when I say ideal gas equation, PV is equal to nRT and it is derived from Boyle's law, Charles' law and Avogadro's law. The point comes is the application of these law to the gases, application of these laws to the gases, to gases. Now, when I say gases, gases existing in the nature, when I say gas, gases existing in the nature are of mainly two types. One, easily liquefiable gases, easily liquefiable gases, and non easily liquefiable gases, non easily liquefiable gases. Now, when I say easily liquefiable gases, by applying the pressure we can convert them into liquid, whereas non easily liquefiable gases is if you apply a higher pressure also, these gases will remain in the gaseous form itself, that is they cannot be liquefied. To give few examples, let me give one or two examples on this easily liquefiable gases and non easily liquefiable gases. If I just take example for easily liquefiable gases are to name a few, we have carbon monoxide, carbon dioxide, ammonia, methane, etc. These are easily liquefiable gases. And non easily liquefiable gases, if I have to give example, all noble gases such as helium, hydrogen, nitrogen, oxygen and so on, etc. So, we have two types of gases, easily liquefiable gases and non easily liquefiable gases. And when you want to apply these laws to these two types of gases, we find that this law, that is Boyle's law, Charles' law, Avogadro's law and equation PV is equal to nRT is applicable at certain conditions of temperature and pressure only, certain conditions of temperature and pressure only. They are not applicable at all temperature, at all conditions of temperature and pressure. So, they are applicable only at certain conditions of temperature and pressure, applicable at certain conditions of temperature and pressure. Now, the quest is to apply these laws or to find out the certain conditions at which these gas laws can be applied, and we can use we can make use of these laws for getting the interrelation between the pressure, volume, temperature, number of moles, which are variable properties of gases. So, when we want to apply this, it is found these laws are not applicable at all conditions, and therefore, one term which is introduced here, that is ideal gas and non ideal gas. Ideal gas is the one, the ideal gas is the one which obeys all these laws, which should obey obeys all these laws at all conditions of temperature and pressure. These laws at all conditions of temperature and pressure, whatever may be the temperature and pressure, this law should be applicable. That is, the PV is equal to nRT equation, Boyle's law, Charles law and Avogadro's law, they should be applicable. But in real fact, we have these two types of gases, and we say that these gases do not obey these laws at all conditions of temperature and pressure. So, we cannot have any ideal gas. Practically, we do not have an ideal gas. It is an imaginary gas. It is an imaginary gas, and all the gases which are existing in the nature, existing gases, and those are either they are easily liquefiable gases or they are non easily liquefiable gases, they are said to be real gases. They are said to be real gases. So, we have mainly two types of gases based on ideal gas equation. Ideal gas is that which obeys Boyle's law, Charles law, which obeys Boyle's law, Charles law, Avogadro's law and ideal gas equation at all conditions of temperature and pressure. And those gases which do not obey these laws and PV equal to nRT equation at all conditions of temperature and pressure is called as real gases. So, here what I say is the real gases behave ideally, that is obey gas laws and PV is equal to nRT equation at certain conditions of temperature and pressure, at certain temperature and pressure. Okay. So, there is no such gas existing in the universe which is ideal. That is the law cannot be applied to the gases at all conditions of temperature and pressure, certain condition of temperature and pressure. So, to find so in the quest of finding that certain condition at which these laws can be applied is under job of the it is a job of the scientist, and two scientists work is accepted and that we will be learning. One is Amagat, another is Van der Waal. These two people, these two scientists, they studied the real gas, when these real gases behave ideally or when these gases deviate from ideal behavior, that is deviate from ideal behavior. Okay. So, we will be learning now the deviation of real gases from ideal behavior from the point of view of Amagat and the point of view of Van der Waal. So, let us start. Deviation of real gases from ideal behavior. Deviation of real gases from ideal behavior. Deviation of real gases from ideal behavior. From ideal behavior. Okay. Now, for this, let me take two types of gases which are existing in the universe. One, easily liquefiable gases. To give an example, we have carbon monoxide, carbon dioxide, ammonia, methane, etc. and non easily liquefiable gases, non easily liquefiable gases. We have few examples here, that is all noble gases, hydrogen, nitrogen, oxygen and so on. Okay. So, deviation of real gases from ideal behavior, we will see all these are real gases, and when these are going to behave ideally, that we shall see. Now, when I want to see this, then I need to know the experiment of Amagat. the experiment of Amagat. The experiment of Amagat we need to know. Experiment of Amagat. Amagat's experiment, or I'll write Amagat's experiment. Amagat's experiment. Amagat's experiments. Okay. What Amagat did was he wanted to see the application of laws. Now, when I say the law, we know the law PV is equal to nRT. All the laws give me the equation PV is equal to nRT, where N is a gas constant, this is constant for a given number of moles is constant, R is constant, at a given temperature T is constant. So, we have a Boyle's law, which says that PV is equal to constant at N and T constant, that is when temperature and the number of moles are kept constant, we have this. So, this real application of this is learnt by Amagat, and what he did is he just found out different values of P1, P2, P3 and so on. Respectively, he find out the values of V1 volume, V1, V2, V3 and so on. He found out respective values of P1, P2, P3, V1, V2, V3, and this give him values of P1, V1, P2, V2, P3, V3 and so on. And what he did is he simply plotted this graph. Now, here according to the Boyle's law, this PV should be constant. That means P1 V1 should be equal to P2 V2, P2 V2 should be equal to P3 V3 and so on at all conditions of temperature and pressure. So, to find out that, what he did is he just took the ratio, the product of PV, and he plotted the graph of PV versus P. He plotted the graph. So, he plotted the graph of pressure PV versus P curves, and these PV versus P curves are known as Amagat's curves. And these Amagat's curves, I will use it for two types of gases here. I will just take one example, say I will choose hydrogen here, and I will choose say carbon, okay, I will choose methane, I will choose these two. Okay. So, what he did is he just took a graph of these. Okay, let us see the graph. The graph appeared like this. Okay, so I will just try to draw a graph here. Okay, so along y axis they took PV, and along x axis he took P. Okay, so I will just take two such graphs I need. Okay, I am just taking one more graph here I need. Okay. So, let us take one easily liquefiable gas and one non-easily liquefiable gas. Okay, easily liquefiable gas I will take here, say non-easily liquefiable gas I will take. Okay, before I take any gas here, if this law is applicable, if this Boyle's law is correct, then the Boyle's law at all conditions of temperature and pressure, whatever may be the pressure, the Boyle's law PV is constant, means P1 V1, P2 V2, P3 V3 should be constant. So, for ideal gas behavior I should get a graph like this, that is the PV should be constant, PV should not change with pressure. So, this is ideal behavior. Or I can say PV is equal to nRT, ideal behavior. This is a curve for ideal gas. Similarly, I will write it here also, this is the ideal behavior. Okay, I will say PV is equal to nRT. Okay. Now, this is the ideal behavior, that means PV should be constant irrespective of pressure if you apply Boyle's law. But what actually happened? If I just say for example hydrogen gas, for hydrogen gas it appeared like this, the graph appeared like this. This is the graph for hydrogen gas. Okay, this is the graph for hydrogen gas. See, this is the graph for hydrogen gas. Okay, and for methane gas, the gas appeared like this, the graph appeared like this. This is for methane gas. Methane gas, I will write CH4 formula, right? Methane gas. So, if you see it carefully, we get some conclusion here from these curves. I will get some conclusion. So, let us try to conclude these. Now, the experiments were performed, different pressures and different volumes were determined, and respectively P1 V1, P2 V2, P3 V3 were determined, and P1 V1, P2 V3, P2 V2, P3 V3, P4 and so on. At different pressures they have determined the graph, and the graph appeared like these. This is for non easily liquefiable gas hydrogen, and this is for easily liquefiable gas methane. If you see it carefully, this is ideal behavior. This is the point at which this curve should meet. These curves should meet at this particular point. At this particular point it should meet. But if you just take hydrogen gas, as the pressure increased, you will find that the gap between the ideal behavior and the hydrogen gas is increasing. That means there is deviation from ideal behavior, as you increase the pressure, and as you decrease the pressure, the hydrogen gas is approaching ideal behavior. It is approaching ideal behavior. So, from this graph I can easily clear that at high pressure there is maximum deviation from ideal behavior. And at low pressure, the real gas approach ideal behavior. It touches this ideal gas behavior equation. So, at low pressure there is the gases approach ideal behavior. So, there is ideal behavior at low pressure. There is ideal behavior of gases. So, we have concluded some point here. So, for hydrogen gas, that is non easily liquefiable gas, there is a deviation. At high pressure. And at low pressure the ideal behavior is there, that is the approach ideal behavior. So, Amagat's experiment is made successful in predicting the condition at which the ideal gas equation PV is equal to nRT can be applied to the real gases. Same thing is applied to the non easily liquefiable gases. He got that at near low pressure, you see the ideal behavior is there. Again, as the pressure increase, you see the gap between the curve for methane and the curve for ideal gas is increasing. So, at high pressure there is deviation from ideal behavior, and at low pressure there is ideal behavior. That is one conclusion was drawn. Further, if I plot this graph at different temperatures, this is at certain temperature, this is at specific temperature. Suppose if I plot the same graph at different temperatures, okay. So, I will just draw this graph at different temperatures, same graph at different temperatures for a particular gas, PV versus P. Okay. Ideal behavior means, PV should be constant. So, I should get ideal behavior. But at certain, okay, now this is the hydrogen gas. This is the curve for hydrogen gas at 200 Kelvin. This is the curve for hydrogen gas at 500 Kelvin. This is the curve for hydrogen gas at 1000 Kelvin. So, if you just see carefully, as the temperature increase, as the temperature increase, the gap between this gap, see, as the temperature increase, the gap between the curve for a real gas and the curve for ideal gas, this gap is decreasing. That means if the temperature is increased, the real gases are approaching ideal behavior, that is, this curve is coming towards the ideal behavior and it is coinciding with the curve at a very high temperature. So they got one more conclusion. That conclusion is, at high temperature there is ideal behavior and at low temperature there is deviation from ideal behavior. Deviation from ideal behavior. So this is the explanation of Amagat's explanation, and Amagat successfully showed that these are the condition at which, so he got some conditions, and these conditions if I combine, then I will see there is deviation from ideal behavior, at low temperature and high pressure, and there is ideal behavior at low pressure and high temperature. That is the practical proof of the condition at which these laws need to be applied. So here we come to the conclusion. So the conclusion says that so Amagat's curves gives us an idea. They imply at, just check, at high pressure, and at low temperature, real gases, whether it is easily liquefiable gas or non easily liquefiable gas, at high pressure and at low temperature, real gases deviate from ideal behavior. And at low pressure and high temperature, real gases behave ideally. Behave ideally means they obey these equations. PV is equal to nRT equation, that is obey Boyle's law, Charles law, and equation PV is equal to nRT. So this is the Amagat's explanation regarding the condition at which the real gases deviate from ideal behavior, and at condition at which real gases behave ideally. So this is the explanation. Now the question comes, why so? We will answer this. So again I will just go back. What he has done, Amagat, he has just found out different values of pressure and different values of volume, and he found out P1 V1, P2 V2 and so on, and he just plotted the graph of pressure PV versus P. These are PV versus P curves, we known as Amagat's curves. He got these curves, and based on this observation of these curves, he got a statement, and this statement is here. Ideal behavior and non-ideal behavior. So they got the condition. At high pressure and low temperature, real gases deviate from ideal behavior, and at low pressure and high temperature, real gases behave ideally. This is Amagat's practical explanation regarding the behavior of gases as far as the Boyle's law, Charles law and PV is equal to nRT equation is concerned. Since Boyle's law, Charles' law and Avogadro's law give this PV is equal to nRT equation, this PV is equal to nRT equation is of important.